So based on the overview video, we now know that we want to be computing the area under some specific curves, and for that we'll use the definite integral. So the definite integral will be used to compute the area under a curve like this one. So I want to bring up the concept of limits for a second, just to show you the analogy between derivatives and integrals again. So remember that whenever we were computing the derivative, or really defining the derivative, we wanted the slope of this tangent line to whatever curve f of x we were considering. And the way that we computed that slope was, first we noticed that because this isn't just a straight line, this doesn't have necessarily a well-defined slope at a particular point until you start taking a limit. So here what we did to compute this slope was we took a nearby point, actually really a series of nearby points, and we considered these lines that connected our point of interest with the nearby point. And we considered those slopes as our nearby points got closer and closer to the point that we were interested in. And in the limit, as those 2 points got arbitrarily close together, we would eventually get the slope that we wanted, which is the slope of the tangent line. So we defined the derivative by using that limit. As those 2 points got really, really close together, the limit would give us the slope of the tangent line that we wanted. But then we used some fancy rules like the power rule or the chain rule or the product rule or whatever in order to be able to compute the derivative without using that limit definition. The definite integral has a limit definition. So in the same way that the derivative had a limit definition, the definite integral will also have a limit definition. The idea here is this: if I want the area under this curve, then I want this area down here. However, if that curve is not a really nice geometric shape, then I don't necessarily have a nice formula for that area. But what I can do is I can squeeze a bunch of rectangles under that area, or under the curve, and then compute the sum of those 4 rectangular areas. And that will be pretty close to the area that I want, but it's missing a little bit. Just like whenever I wanted the slope of the tangent line over here, I could take a nearby point and compute that slope. That slope won't be exactly the slope that I want, just like this area isn't exactly the area that I want, but I can take a limit in order to get the one that I actually do want. And I can do the same thing over here with these rectangular areas. I can take the limit as I get more and more rectangles squeezed under this curve. And as I take more and more rectangles, my approximation for that area becomes more and more precise. And in the limit, as the number of rectangles goes to infinity, I'll actually be able to recover the exact area under the curve. So I would want to take that limit as the number of rectangles goes to infinity. And it actually doesn't matter which kind of rectangle approximation you use. So you can use the left endpoint of each rectangle to touch the curve, you could use the right endpoint of each rectangle touching the curve, or you could use the midpoint of each of these tops of the rectangles touching the curve. Either way, you'll end up getting a perfect approximation to that area whenever you take the limit that we're considering. So that would be the limit definition of the definite integral. But just like with derivatives, there are some fancy rules that allow you to compute those integrals without using the limit definition. And for a couple of reasons, we're going to skip over the limit definition and jump straight into the nice rules when it comes to integrals. So one reason is that the technical definition for integrals is a little bit too complicated for this class. And then another reason is just that we don't have time to go back to limits at this stage in the class. So lucky for you, we'll just dive straight into using these nice rules for computing these integrals, and you won't need to worry about limits. But I do want to emphasize that integrals, just like derivatives, are technically defined using limits, And then we find some nice rules that allow us to circumvent the definition and use these nice convenient shortcuts to actually compute the derivatives or the integrals that we want. So here's what we're going to be using as our definition for the definite integral. So the limit of those rectangular areas is going to be called this definite integral, and a definite integral will have bounds a and b. So those are these lower limits and upper limits of integration. So that's what distinguishes it from an antiderivative like the ones that we've been considering in the past couple of lessons. But these are closely related by the fundamental theorem of calculus. So I'll postpone talking about that until we make it to that theorem, but let's define some terms. So we've actually already talked about the integrand. That's just what I'm calling the inside of the integral, or the function that you're integrating. We've seen that dx is the differential. So that's this thing out here. That tells you which variable you're integrating with respect to. So this would be an integral with respect to x. And that's useful whenever there's more than one variable in the function that you're considering. And then the new things for today are these lower limits and upper limits of integration. So those tell you the two bounds on the sides where you want the area between. So in terms of, let's just look at this picture here. If we wanted this area, then what we would do is we would consider these bounds of integration. So this side over here, I know you probably can't read this on your screen, but this is x equals -3 on the left side, and then this vertical bar would be x is equal to 7. So if I wanted the area between those two bars, the way that I would write it is as the integral from -3 up to 7. So those bounds of integration are going to tell you the two boundaries between which you want the area. And then we would say whatever function we want to be integrating, and then the variable that we want to integrate with respect to. Now, there is one little point that I want to observe here, which is that the areas for which the y value is negative are going to be counted as negative by the integral. So if the function dips below the x-axis, then that counts as a negative area as far as f of x is as far as the definite integral is concerned. So anytime you have areas beneath the x-axis, they count as negative areas. Areas above the x-axis count as positive areas. But otherwise, this is sort of the normal area that we would be considering. Okay, so those are the basics of definite integration. And now, just to test that we know the terms that are involved, let's talk about these first three problems. So in problem 1, it says, what's the variable of integration here? There are 4 variables in this expression. So there's r, there's s, there's u, and there's y. So we need to decide which one of these is the variable of integration. S and r are the limits of integration, or the bounds for this integral. So those are not going to be what we're integrating with respect to. U is a variable in this function that we're integrating, but we're not integrating with respect to u, we're integrating with respect to y. So the giveaway in all of these is just going to be that if you see a dy at the end of the integral, that tells you which variable you want to be integrating with respect to. So y is the variable of integration because the differential is dy. So that means that if we were to start computing this integral, I would treat u and s and r as constants, and y would be the thing that I treated as my variable. Just like if I was integrating something like 5t dt, I would treat t as my variable, and this would be something like a 5t squared over 2 plus your constant. So t would be your variable of integration in this example, y is your variable of integration in problem 1. In problem 2, remember the integrand just refers to the function that's being integrated. So the integrand here would be 8 over u squared. And we're going to need to deal with some negative exponents in a second, so just let me remind you that if you wanted to write this all on one line, you could rewrite this as 8 times a u to the negative 2, because a negative 2 exponent tells you to first take the reciprocal of u and then square it, so that these are equivalent expressions. And then in problem 3, we want the limits of integration. There are 2 limits of integration. That's the upper bound and the lower bound. So I would say that the limits of integration are 0 and 5. And in terms of the picture, what this is saying is that if you graph the function 5t squared, it would look something like this. If the x-axis is represented by t and the y-axis is represented by the value of this expression, I guess I should say the y-coordinate is the value of that expression. But this is telling you the area between 0 and 5 underneath this graph. So we would look at the t value 0 and then the t value 5. Those are going to be your bounds of integration, and this integral would be computing this shaded area, the area underneath your curve between 0 and 5. So in the next video, we'll start getting onto properties of definite integrals, and we'll start computing these integrals. Whoops.